4.7, the law of sines and the law of cosines. So we have spent a couple days looking at right triangles and how trigonometric functions work for right triangles. So one of the big questions then is, how do we figure out stuff about triangles that are not right triangles? And that means now we're talking about oblique triangles. So when we're working with oblique triangles, we have other ways to go through and figure out the sides. So this is oblique triangles, triangles that are not right triangles. They could be acute, they could be obtuse. And our first rule, or our first property that we're going to use, is law of sines. So law of sines says that if I take the sine of angle A, and notice for angle A, I have a capital A, and if I make a ratio out of that and put it over side A, which is across from it, then it's going to be equivalent to the sine of angle B, which is over side B. So the way we label these triangles is we always have the capital letters for angles and the lowercase letters for sides. And the way we label them is our angle A is across from our side A. So this is law of sines. So when we say sine of A, we mean like literally whatever this angle measure is, like say it's 37 degrees, that you're using the calculator button sine and you're taking the sine of A and it's going to spit out a number at you. So we're not talking about a trig ratio of sides because we don't have a right triangle. So this is one way to figure stuff out, is we can make proportions and use this to solve. So we're going to go ahead first and use this to solve a triangle. So when we say solve a triangle, we mean find all the angles and all the sides. So I have angle M, I have angle L. N should be pretty easy then, right? So for angle N, we would just take 180 because all the triangle angles should add up to 180, and we would subtract the 112 and the 29. So angle N is going to equal 39 degrees. So we've got part of our answer, but we still have to find a couple sides. So law of sines works really, really well for sides. So we're going to take the sine of, let's see, 22 is the side we have, and the angle that would correlate with that would be 29 degrees. So we'll say the sine of 29 degrees over 22 is going to equal, and now we have to decide if we want to solve for M or N first. I'm going to solve for M first, I think. So that means my sine of angle M, which is 112, should go over that little m. So now to solve, I need to do cross products. And when I do cross products, I actually can then switch which side my variable is on. So I'm going to do the sine 29 times m. So m times, so I'm basically multiplying these two, and then I'm going to do equal, and then I'm going to multiply these two. Means extremes theorem. So m sine 29 degrees equals 22 sine 112 degrees. And this is how I'm expecting you guys to show work. And then I need to divide both sides by the sine of 29 degrees. So m equals 22 sine 112 degrees over the sine of 29 degrees. So this is your calculator ready form. So I need to see this part of your answer. Calculator ready. You don't have to label a calculator ready. I'm just trying to make sure that you understand what I'm looking for. And then I also need you to come up with an answer. And here it says that we're going to be rounding side lengths to the nearest tenth. So when I plug this into my calculator, I get 42.1. So this is my actual answer and my calculator ready part. Most of the points come from just the calculator ready form. So if you've got an issue with using the calculator at the end, you'll still get most of the points. All right, and then I still need to find side N. So I'm going to go back to using that same ratio, sine 29 degrees over 22, because that's the side, 22 is a side that I don't have to round or anything. I don't want to use a 42.1 for this. And then my sine of angle N, which is 39 degrees, over N, which is actually what I'm looking for. And then I'm just going to solve it the same way. I will use cross products or mean extreme theorem. So N sine 29 degrees equals 22 sine 39 degrees Divide by the sine of 29 on both sides to get that calculator ready form. And then n is approximately equal to 28.6. All right, so we found all the angles and all the sides. We have solved triangle LMN. So it's a little bit different. I'm going to back this up a step. When I am using law of sines to find an angle, and there's a reason for that. If I take, let's say, the sine of 20 degrees, so this is just like extra stuff to help you understand something that we're about to do. And it'll really make more sense with things that we learn next week. So if I do the sine of 20 degrees, I get 0.342. Okay, so 180 minus 20 equals 160 degrees. So let's look at what happens when I do sine of 160 degrees. Let's go ahead and do that on my calculator. What does that give me? Sine of 160, and my calculator is kind of off to the side, so of course you can't see it. Sine 160. Oh goodness, I get the same thing, 0.342. So how about if I do sine of, let's pick 40 degrees. What would 40 degrees be? And sine of 40 is 0.643. How about sine of, let's see, 180 minus 40 is 140. So let's say sine of 140 degrees. Oh man, I get the same answer, 0.643. And these are both small enough, 40 and 140, that they could be angles in a triangle. So we have this weird thing that because we can take the sine of different angles that are both pretty small and get the same answer, that there's a little bit of weirdness when we're using law of sines to find angles. So let's think about law of sines again. Law of sines is that if I take the sine of an angle over the opposite side, it's going to equal the sine of a different angle over that opposite side. But if I am solving for this angle instead, somewhere I'm going to have to do a sine inverse. And when I do a sine inverse of, say, in this case, 643.643, how do I know if the angle is going to be 40 or 140? What exactly is going on? And so there's some weird stuff that can happen when we're using law of sines to solve for angles. So you really didn't need to draw or write out anything that I did on this page, but on the next page, we'll look at the different cases and what can happen. So for example 3, and they're going to give you kind of a clue in the directions. It says, find all solutions for the given triangle if possible. If no solution exists, write no solution. Round side lengths to the nearest tenth and angle measures to the nearest degree. So sometimes when you're using law of sines to solve for an angle, you'll get one answer. Sometimes there'll be no triangle at all. And sometimes there's actually going to be two angles that would work, that would give you the same answer for sine. And that's what we looked at just a second ago. So let's go through and set this up. So we still set it up using law of sines. I could draw out a triangle, might be kind of helpful here to look at, but I know that A is across from A. So if I say sine of 63 degrees over 18, that's going to equal sine of, this is a little b, so sine of B over 25. And then I would do cross products. So I'll have 18 times sine B equals 25 times sine 63. Cross products are means extreme theorem. And then my next step is always to divide. So I'm going to divide by 18. So sine B is going to equal 25 times the sine of 63 degrees over 18. So if I have a sine of an angle, but I want to know that angle, I really need to do sine inverse on both sides. Because if I do a sine inverse of the sine, I'm just left with B. And then the other side, I'm going to have sine inverse of all this stuff, 25 sine 63 over 18. So it's not our favorite thing to do, using law of sines to solve for an angle. We know there's going to be some ambiguity. They'll talk about the ambiguous case. But I'm going to show you exactly how we're going to handle this and all the different things that can happen. So when I plug this in on my calculator, it says domain error. So what that means is that the triangle does not exist. So when I plug this into my calculator says like error or domain error or something like that. It could vary from calculator to calculator. So what that means is there is no triangle. No triangle that works and actually does this. And so what that means is that there is no solution. So you don't have to write all this. I just want to make sure that you're really clear on what's going on. So I would need to see this part. I would need to see your calculator ready form. But then your final answer is that there is no solution. Or you could say triangle doesn't exist, honestly. So sometimes that will happen. So sometimes that the measurements that they give are not even going to work for a triangle at all. So let's look at another case. I think we're actually going to jump down to C right away, which is going to kind of mess you up. But let's see, for C, we would do sine of 45 degrees over 18 equals sine of whatever B is over 24. So let's go through and work this out. So 18 sine B equals 24 sine 45 degrees. Make sure you get that degree symbol on there every time. Remember, if it doesn't have degree symbol, you're basically telling me it's not degrees, it's a different measurement, it's radians. We'll learn about radians next week, but for now, just make sure you have a degree symbol. So divide both sides by 18. In order to get rid of the sine, I need to take the sine inverse on both sides, and so then B will equal the sine inverse of 24 sine 45 degrees over 18. So when I work that through on the calculator this time, I get 71 degrees. So when we get an angle, that's all fine and good. I've got a solution there, but we have to make sure that there's not more than one solution. So I'm going to write or, and I'm going to just include a question mark because we're not really sure if there's going to be a second angle or not. But my second angle would be 180 degrees minus the 71 degrees. Remember, that's how I got those equivalent signs on that last page when I was just kind of doodling around there. So 180 minus 71 is 109 degrees. So I'm thinking that B could also equal 109. But I need to check my original triangle. I need to make sure that 109, so I probably shouldn't have boxed it in yet. I need to make sure that 109 could actually work. So let's look at my angle. I have 63 so far. So, does 109 degrees work? So if I have one angle that's 109, because that's going to be my angle B, let's call it, not just B, let's call it B sub 2. And I have my angle A that was 63 degrees. Sorry, I'm having to scroll up and down. Then what would angle C equal? Well, in that case, angle C, is there even enough left over? Because if I add these two and it's already over 180, then I know that it can't even work, right? There can't even be a third angle. So 109 plus 63 is 172. That would mean that angle C would be 8 degrees. So it's a small angle, but it works. And I'm going to go ahead and call this C2. So I could have a B, I could have an A, I could have a C. They could all work if B is 109. So that is going to be my second answer. And then if I was going to finish this problem, I've already got side B, I'd have to figure out side C as well. And we're not actually going to do it because I think you could figure it out. You would just have to do another law of sines. You'd have to have like sine 63 over that side as sine 8 over the other side. So you could figure out your second side as well, assuming that we use the 109. But our original angle there that we actually solved and got with our calculator, our B1 was 72. And so for that one, you'd have to go through and solve the rest of the triangle as well. Like I said, I don't really want to solve the whole triangle here. I just want to do that one side, that ambiguous part, and kind of get you on your way there. So let's look at one more scenario. So for this one, I would have sine of 105 degrees. These are pretty long notes because we still have a couple more formulas that we're working with. Over 73, I'm writing at the top of the surface. Top of the page never goes as well. And then sine b over 55. So let's try this one. So 73 sine b equals 55 sine of 105 degrees. Divide both sides by 73. So sine b equals 55 sine 105 degrees over 73. And then I would have to do my sine inverse on both sides. So b will equal the sine inverse of 55 sine of 105 degrees over 73. And when I do that, I get that b equals, let's see, b equals 47 degrees. So, and then here's my two parts to this one. So for this one, I don't even know where to do this work. I did not leave myself a lot of space here. So let's also check, maybe we'll put it over here. Also 180 degrees minus 47 would equal 133 degrees. But if I look at how A is already 105, if my B, or in this case B2, was 133, both of those angles together are already, when I add them, more than 180. And remember, the maximum degrees, that degrees, I guess we shouldn't say maximum, we should say the degrees of a triangle when we add them together equal exactly 180. So it's over that 180. So if I add 133 and 105, I'm already at 238. And because that is more than 180 degrees, it's not even possible. So this is not possible because it would be too big. So in this case, I really only have one answer for B. So B is only going to be 47 degrees because that second angle was too big. So this is how we kind of have to go through this. It's great if you get something that's no solution, then you know triangle doesn't work. That's how that is. If you try to get that second angle by doing 180 minus and it's too big, your angles add up to be more than 180 to start off with, then you can say there's only one triangle, there's one answer for B, but then sometimes that second angle will also be a viable solution. Remember, 109 wasn't too big, it still allowed us to get C2. And so then you have to keep solving and you're going to have two sets of measurements for that triangle. So we don't always have that information. We don't always have an angle and then a side opposite from it. And so sometimes we need to have a different way to figure this out. And so we get law of cosines. And law of cosines is a hard one to remember. So we're really going to look for a pattern in these variables. I didn't write it down the three different ways. This would be solving for side C. We could also write an equivalent of formula solving for A or B, but we just really want to look at this. So cosine of C, so here's my angle C right here. And if I look at A and B, those are the sides that are included on that angle. They are adjacent to that angle. So if this is my angle C, A and B are going to be my included sides. For this angle. And it solves for C, which is opposite of the angle. So opposite of angle. So opposite of the angle I am working with. So we won't always be solving for side C. And like I said, it's really better to memorize the pattern for how this equation works than it is to just memorize letters every single time. So I have a squared plus b squared minus 2ab times the cosine of c. And again, a and b are going to be those included sides for that angle. And then it solves for c, which is the opposite side. So law of sines works really well for what we had last time. This one is really, it's different, right? This is when I'm looking for a third side. I'm not looking for angle B. I'm not looking for angle A. All I've got is this angle right here, and I have two sides to work with. I don't have like an angle and a matching side. If I had an angle and a matching side, then I could use law of sines, but I don't have that here. So it's different beginning information. So a lot of times you're going to look at a problem and you're going to have to figure out, well, can I do law of sines? Can I do law of cosines? Like, what information do I have? And if I had side C and angle C, then I could really use law of sines here, but I don't have that. I just have an angle on the included side. So that's when I need to use law of cosines. This is really just the same formula, but rearranged so that you could solve for the angle instead. And your book does not have this in it. So I would make sure to write this down. I find that students have a really hard time. I know you're thinking, but not me. I could totally do this. Working with this formula and solving it for the angle instead, but it seems to be really difficult for people, especially because of sign issues. So it's going to be better to just have at least one version of this. Again, we could make this for cosine A or for cosine B or for cosine C here like we have it. But we really just want to look at it one way and then kind of use that pattern to find all those other formulas if we need them. But we want to just memorize it one way and then understand how it works. So I really like this angle one. All right. So now we're going to actually use law of cosines. So on this one, I have an angle A. And I'll notice that 14 and 12 are my included sides. I can't use law of sines because I don't have like angle A and side A. And I want to solve the entire triangle. So I am going to use law of cosines. So law of cosines, if I am looking for my A, and in this case little a squared, that means I need to have those included sides b squared plus c squared, so 14 squared plus 12 squared minus 2 times those two included sides times the cosine of the angle. So let's plug in here as much as I can. I'm going to square the 14 and the 12. So that's going to be, let's see, 14 squared plus 12 squared is going to be 340. So I'm doing just a little bit of the algebra, so I'm not plugging this whole big thing into my calculator. So I'm just doing the easy parts. 2 times 14 times 12 is 336. If I put something really giant into my calculator, I risk a lot of errors, but I also risk more errors if I don't put enough in there, right? We've got to make sure we have parentheses in the right spot or that we want the order of operations to work out correctly. So this is going to just be perfect for me. And I know that my A is only going to be positive here. So I'm just going to do on my calculator the square root of 340 minus 336 cosine 39.4. Because I can reject negative answers here. So A is 8.964458673. Really, when I am continuing on and solving the rest of this triangle, I should use this long version of A, because as soon as I round it off, my answer is not going to be very accurate anymore. But this is really all about process. And I am okay with you just rounding it at this first step. They want nearest tenth, but this 9 would actually go up, so it's going to be 9.0. I have to have the 0 there to show that I've rounded to the tenths position. So I'm just going to use A as 9 in the rest of my problem. So my answers might be off a little bit from the textbook, but that's going to be okay because we're really kind of process driven here. It's not all about having this exact beautiful answer. It's not like statistics right now. We're really just after the process. In a science class, that would absolutely not be okay, but we are in a math class, and for our purposes right now, it's going to be okay to round that and then use that rounded number. So I can, now that I have side A and angle A, I could use law of sines to find either angle B or angle C. But I know that when I solve for angles, it's ambiguous. I could have one triangle, I could have no triangles, I could have two triangles, and I really don't want that. So instead, I'm going to use my cosine formula, my law of cosines. So cosine C equals, so I'm going to use cosine C, which is just the one that we wrote down on the other page. So then that's going to equal those included sides, 9 squared and 12 squared, so 9 squared plus 12 squared, minus the square of that opposite side, so minus 14 squared, over 2 times the included side. So 2 times 9 times 12. And then I'm going to go through and figure out the numerator, figure out the denominator. So my numerator, 9 squared plus 12 squared minus 14 squared is going to be 29. The denominator is 216. And then I would take a cosine inverse on both sides. So C is going to be cosine inverse of 29 over 216. So again, I could use law of sines to get this, but then I have to worry about that ambiguous, is there more than one answer? So law of cosines will only give me one answer, even though it's a little bit more complicated, and I get 82 degrees. And just so you understand, because I rounded and made this 9 instead, I believe the book answer was actually 83 degrees. So I end up being a little bit off. So if you really wanted to be super accurate, if that was important to you, you would keep, because like for sides, we want 10th, I would keep like maybe 3 more decimal places. And I would work through the whole problem with that really long number. And then at the end of it, I would have to go through and round everything as my final step. So last thing I need to do is find angle B. And so 180 would be the total measure of the angles in my triangle. And I have to subtract C, which is 82. And I also have to subtract A, which was 39.4. It's really weird on this problem because they want nearest degree, but they're giving you an angle that's not nearest degree. So it's kind of awkward. So I get 58.6 degrees, but again, they asked us to round. So I'm going to call B 59 degrees. So we have now solved our triangle. Next is Heron's formula. So this is to find an area of a triangle that is not a right triangle. So once again, we're looking at oblique triangles, and what do we do when we don't have a right triangle? How can we do things like find area, or like on the last two where we looked at solving for different sides or different angles? So now I have Heron's formula. So here's my area formula, and it says S is 1/2 of the A plus B plus C, which is really basically half of the perimeter. A plus B plus C would be the perimeter of the triangle. And the 1/2 in front of it means I'm doing half of the perimeter, which they call semi-perimeter. So first we find S, and then we have this formula where it says area is square root of S times S minus one of the sides times S minus the other side times S minus the third side. So that's Heron's formula. We're going to do a quick Heron's formula example. Area is a lot easier to do than solving a triangle, right? We only have to find one thing. So we recognize here we've got all 3 sides. If I had a right triangle somewhere, I would do that instead, but I don't have a right triangle. So Heron's formula it is. So first, I'm going to figure out the semi-perimeter. So I'll do half of all those triangle sides added together, 44 plus 53 plus 47, which is really nice numbers. 53 and 47 make 100. Plus 44 is 144, so half of 144 would be 72. So that's my semi-perimeter, and then I find my area. Let's see if it'll let me scroll up yet. So area is going to be square root of that 72 times 72 minus each of those sides. So 72 minus 44, 72 minus 47, and 72 minus 53. Your book gives some good proofs of stuff. If it bothers you for me to just be like, hey, here's a formula, follow formula day. If you really are one of those people that likes to know why or what's going on, your book does give some good stuff on where these come from. But from my point of view, like this is all about process and finding things. It's not really about where these formulas come from. So I'm just going through and subtracting. And I did cheat and use a calculator. So I have 72 times 28 times 25 times 19. And I'm going like, oh man, that 25, I can take the square root of that right away. That's just a 5. So basically I'm going through and simplifying this. 72 is 36 times 2. I can do the square root of a 36 also. 28 is 4 times 7. I can do the square root of a 4. And then 19 is just a prime. So let's see. I can take the square root of 36 and the square root of 4. So my area is going to be 5 times square root of 36 is 6, square root of 4 is 2. So that's going to be all the whole stuff out in front of my square root. And then inside, I'm going to be left with the 2 and the 7 and the 19, which are all prime numbers. So let's see. 30 times 2 would be 60. 2 times 7 times 19 is 266. So whenever we can leave an answer as exact, this is an exact answer. Exact answer means I did not use a calculator. As soon as you use a calculator, you're rounding something. Even if you write down all the decimal places your calculator spits out at you, it's no longer exact. So this is an exact answer. And we're going to try to do that as much as possible. So I'm going to leave my answer that way, just simplified. In math, we think they're really pretty. And this, again, is where we differ from science people, right? Because this is not an overly useful answer for them. So if you're in science, you pretty much always just take the decimal. But we're in math, so we're happy with that. So now we're going to look at what happens if you want the area of a triangle, but you don't have all three sides. So here is another way. And again, your book will give you history, kind of not really history, but how you derive this basically. So this is for side, angle, side. So again, this is when I have an angle and an included sides. So here, if I take the sine of A and I multiply it by the included sides and by 1/2, so it kind of reminds you of 1/2 base times height, I can find the area. So it's just when you're given the same stuff basically as you would for law of cosines, where you've got an angle and the included sides. So I wouldn't memorize it as 1/2 BC sine A. I would think 1/2 included times angle or something like that. So that's exactly what we have here. I've got angle A is 25.89 degrees, and I have those sides. So I can find my area. Area is going to be 1/2 times 52 times 39 times the sine of 25.89 degrees. And they say nearest tenth here. So let's see, when I plug this in my calculator, I get 442.75786062. So I do need nearest tenth though, so I'm going to call this 442.8. And I guess I should probably write unit squared. I did not on the last one. Sorry about that. But our area would be unit squared. So these are actually pretty short. This is the end of our 4-7 notes. So it's basically just those 4 formulas that you have to figure out how to apply and work through. I really think the ambiguous case for sine is going to be the trickiest thing. That's probably going to be what you have questions on.